Saxon Advanced Mathematics, Lesson 85. Hey, are you ready to give your brain like a really good workout? Because I've got a lesson for you. It's a two-parter. The first one is advanced trig equations, not trig identities, although we will be using identities to solve the equations, all right? So not the identities where we're proving that one side equals the other side, but old school equations. They'll come back to you. Grab your page of trig identities. Make sure you have that handy. And make sure that you also have your unit circle. All right. So I'm getting myself organized too. There's my unit circle. My best trig identity page, I have to open the book. Hang on. Okay, so allow us to begin. Seriously, you know, they'll like open the window and get some fresh air because this is kind of a lot, this lesson. Okay, example 85.5. John gives us very little heads up, but just a reminder that we will be using identities in the equations. I got a new green pen. They didn't have any of the green colors I prefer. I had to go with this sort of like, it's kind of like an evergreen, kind of a deep teal. It offends me a little bit, but I'm trying to get over it. Solve. There's an equation. Tangent squared, secant are the two functions. We're also told that this is a tip to us. This tells us that we're going to be solving for theta. Okay, that makes sense. We're going to be solving for that angle, and that we can limit it to one spin. Okay, good to know. We're just going to kind of put that on the back burner and see what we can do with this monster before we go any further. Now, John did tell us that we could use Pythagorean identities in our equations. So what I'm doing is I'm thinking, is there some way we can turn this tangent into a secant? Because then it would match to that, okay? Can we link those two? And this is the one I want to change because this is the one that has the square, right? And Pythagorean identities all have squares. So here's my list of Pythagorean identities. Dang, make sure you're memorizing these, please, because it'll be on the test that you'll need to fill this form out. And remember my daughter's story about getting further on into calculus and physics and saying, ugh, I wish I'd started memorizing back at the beginning when it was still manageable, because now my head is so jammed full of these suckers that it's hard to keep them all straight. And I've talked to a number, it's really interesting, I've talked to a number of my students in this class who are telling me they're interested in studying physics long term, which I think is really cool. Pure science, I love it. But you're going to need the trig identities, so please do yourself a giant favor and just memorize them now. Okay, so we want to turn this tangent squared, ideally, into a secant squared, so it could be friends with that secant. So I look and I go, oh yeah, sure enough, look right here. I would want this form of it, right? I can see it relates tangent to secant, so I just look through. I want to use this form of it because I want to swap out my tangent for a secant. So I'm going to copy the trig identity here. It is tangent squared theta equals okay. And do something to show that that's a trig identity. I guess today I'll put some brackets around it, and I'm gonna write Pythag. So that anyone who looks at this can see, oh yeah, that's a Pythagorean identity, and she's using that to swap that out. Now I'm going to put that in here. And I'm going to use parentheses. And the right side stays the same. Okay, now I'm going to distribute this. And I'm going to bring these guys over because I want everybody on the left side. So it's going to be 3 secant squared theta minus 3, right? That's the second part, minus 7 times the secant of theta, and then this will be plus 5 equals 0. Okay, so distributing and swimming everything to the left at the same side. Then I guess I better fix these two like terms, right? So then I'll have 3, whoops, that should be an S, secant squared theta minus, I'm going to put them in order also, secant of theta, and this will be plus 2 equals 0. Now, tell your brain to get ready to switch gears. What we see here is we have a squared, plane, and none situation with our secants, right? Secant squared, secant to the first power, no secant. What we recognize, and this is a jump, is that we can factor this just as if these were x's instead of secants. So what I'm going to do is I'm going to switch to a more basic algebraic format just to explore how the factoring is going to work, and then I'll go back to this. So this is just me working out the factoring in a simpler, more algebraic context where I don't have to keep writing all of this out, and it looks more familiar to me. Now, I see that I can't factor this directly by inspection because I've got a 3 here. I could use the man-eating dragon, or complete the square for Lord's sake. But there is a possibility that we could use advanced factoring. We learned advanced factoring at the end of Algebra 2. You know, it's probably after spring break by the time we learned it, and a lot of students find that it doesn't really stick in their brains very well. So you might not remember this, and I will have to explain it to you. We can solve, it's called advanced factoring by inspection. What we do is we multiply a times c together. Remember, this is ax squared plus bx plus c equals 0. We multiply the a and the c terms together. We get 6. And then we're looking for a pair of numbers that will multiply to 6 and add to minus 7. So we can easily see that's minus 1 minus 6. Now, what we do is we rewrite this middle term using these two, like so. 3x squared, and we can do them in either order. Minus 1x minus 6x plus 2 equals 0. See how I split this? Minus 1x minus 6x, that equals minus 7x, so we're fine. But what I did was I used these numbers, split it apart. Now I'm going to factor by grouping, like so. For this first one, all I can take out is an x, and I'll be left with 3x minus 1. And here, I'm going to take out a minus 2 because I want to change the signs on this, and I want this to be 3x minus 1. Do you remember that at all? If not, I just explained it to you. Now we can rewrite this as x minus 2 quantity, 3x minus 1 quantity equals 0. And then we can take it one step farther and say either x minus 2 equals 0 or 3x minus 1 equals 0. That's our zero product theorem. If 0 is our product, then either this factor has to be 0 or this factor has to be 0. And then we get x equals 2 or x equals, let's see, we would add the 1 and then divide by the 3. Okay, this is all algebra that we did to help us factor this expression that's very similar to what we just did. What that tells us is that the secant of theta, yeah, it's theta in this problem, secant of theta is either equal to 2 or the secant of theta equals 1/3. Let's go to the top of the next page, right? So now I'm taking these answers and I'm putting them back, kind of. I'm using these solutions to say I just solved that. So either secant of theta equals 2 or the secant of theta equals, what was it? 1/3. All right, so we're ready to look at our unit circle and figure out, okay, so what are the angles that would give us those secants? But I have to ask myself, and I hope you ask yourself too, what the heck is a secant? I forgot in all of that crazy factoring. Help me remember, what even is secant? So we go back to our reciprocal functions, and we go, oh yeah, secant is 1 over cosine. Okay, so I'm gonna write that up here. Secant of theta equals 1 over cosine of theta. So we're looking for angles on our unit circle where the cosine would be, for this one, if the secant is 2, then the cosine would be 1 over 2, right? And if the secant, if the secant is 1/3, then the cosine would be equal to 3. I'll put theta in, right? Because these were our two answers from the bottom of this page, 2 and 1/3. Okay, we factored them as x's, but really they were secants all along, right? So we put them back into the secant form. Then we use this to go, okay, well, so we have to flip this number in order to get the cosine value. Cosine is equal to 3. Now we know this is not possible. Cosine is never 3. It's never greater than 1, right? Cosine cannot be greater than 1. So this is impossible. Now, cosine of 1/2, we definitely have got those. So here's my unit circle. Cosine is the first number, so let's book around here. We need positive. Cosine 1/2, 60 degrees is one of our answers. Theta equals 60 degrees. And let's see, where else would cosine be positive? Cosine is positive in the 4th quadrant, right? And so we know we want the blue angle. That's why the color coding is really nice. There's another positive 1/2. 300 degrees is our other answer. So this is the answer to this wacky problem of ours. All right? I think the trickiest part of this problem, using the Pythagorean identity to switch it from tangent to secant, that's not super hard. The hardest part is knowing that we can take this and factor it using our algebra skills all the way down to the solution and then take these values and recreate, put them back into the secant part of the problem. Do you know what I'm saying? That's a mind bender, isn't it? That's a real mind bender. You probably didn't remember, maybe, I'm not trying to insult your retention, but this advanced factoring by inspection, that might have been a bit of a stretch for you too. So, but that shows up in these problems fairly often. So we have to keep that in mind. I also want to remind you of one other thing I mentioned here. Cosine is never greater than -1, or 1, and it's never less than -1, right? And we can remember that thinking of our sinusoids. Sinuses. When we have a center line of 0 and a normal amplitude, cosine and sine are never going to go above 1, and they're never going to go below -1. So when we get values like this, that cosine is equal to 3, we know, no, that's not going to work. That's not a real thing. Okay, let's try another one. $85.2. John says, solve. Well, he's to the point, isn't he? Equals. And again, we get 0. Okay, so this tells us we're going to be finding angles. We'll be finding some sort of trig function and then using our unit circle to find out which angles will answer it. We only have to include one spin. As I wrote down the problem, I noticed, oh look, there's a squared term and a plain number term and a plain number. No, a squared term. It still has the variable but without the square, and then the plain number. That gives us that pattern of like x squared plus x plus a plain number, and it makes me think, oh, we're going to be factoring again. Pythagorean, though, is going to be our first tool because we can see we're mixing sines and cosines, and that's not cool. That's not going to help us factor. We need those to be the same. And we know, oh yes we do, that there's a Pythagorean formula that will link us sine to cosine. It's the very first one, right? Here it is in this form. We don't want it like that. We want sine squared by itself, right? So that we can put that in. So let's use, again, I'm going to write the Pythagorean. I want to write the whole thing this time. This is the identity we're going to use. Sine squared, I'll use x, equals 1 minus cosine squared x. Remember, we choose to change this term because it's got the square, and we know that all our Pythagorean identities are squares. And then we say, okay, what do we want to relate? Sine and cosine? Ooh, yes, we do have one that does that. Tangent and cotangent go together. No, cotangent and cosecant go together. That's so random. And then tangent and secant, which is the one we used the last time. So John set these up so that we'd be all ready to substitute. And so now we're going to substitute this in here. So it's 2 times 1 minus. And I'm going to swim these over this time. I'm going to put this one next, 3 times the cosine of x, and then this will be last, and now it's equal to 0. All right? I know I'm going to want everything on the left because we're going to try and factor this bad boy. Now, I'm ready to distribute this. Okay, I can see I've got some minus sign drama here, so I'm gonna eventually deal with that. But first, let's combine the like terms. So now I have minus 2 cosine squared x minus 3 cosine of x. These two together to make what? Minus 1 equals 0. And now I'm gonna multiply everything, both sides, by minus 1. Okay, I'm going to put parentheses around it so it doesn't look so lost. That will clean up these minus signs that I don't, this one is the one that's really killing me. So now I have 2 times cosine squared x plus 3 times cosine of x plus 1 equals 0. Beautiful. John has once again set us up for an advanced factoring pattern. We can't use basic inspection because of the 2 here, But we don't have to break out the man-eater, the man-eating dragon, which is the, I can't think of the normal name of it, quadratic formula story behind that, but I always call the quadratic formula the man-eating dragon because it's big and scary. But we're going to try advanced factoring this. We multiply, this is the A term, this is the C term. We multiply A times C and we get positive 2. Now we're looking for numbers that multiply to 2 and add to 3. Okay, well that's straightforward. It's 2 and 1, right? So now, what we want to do is we want to switch this into simple math. So 2x squared plus 3x plus 1 equals 0. Now we can use this factoring pattern. We'll split this into a 2x and a 1x. I like to just write the 1 even though we don't need it. It just helps my brain stay, it helps my brain keep moving really quickly through this part because I don't want to get bogged down here. This is supposed to be the easy part, right? So I'm trying to make this easy to myself. Seeing those ones there make it super easy to factor. This is a plus. This is a plus. It looks almost like a minus. All right, so now I need to factor. I'm going to pull 2x out of that, and I'll have x plus 1. And there's nothing to pull out of that, so I'll just pull a plus 1, and I'll get x plus 1 equals 0. Now we get 2x plus 1 times quantity x plus 1 equals 0. That means either that equals 0 or that equals 0. So 2x plus 1 equals 0 or x plus 1 equals 0. Now I will subtract and divide away any coefficient. I get x equals minus 1/2 and x equals minus 1. Okay, that's the end of my algebra breakout. Now I'm going to take these values to the top of the next page, but I'm going to plug them in. I'm going to call them cosine now instead of just plain x, right? X stands for cosine. So that means, and we're using x as our value for that. The cosine of x equals either, what were they, minus 1/2, or the cosine of x equals minus 1, right? Minus 1/2 and minus 1. Okay, great. Now, this one's a little bit easier. Last time we had what, secant? And so we had to think in terms of reciprocal, but this time we have cosine, which is right on our circle here, so we're fine. Where does cosine give us a minus 1/2? Look, there's one right there, 120. So I'm going to copy, there's my 120. Here, I'll turn it so you can see it better. Minus 1/2 for cosine at 120 degrees. And we remember we're keeping these to under 360, so that's fine. Where else do I have a minus 1/2? Here's one, minus 1/2 at 240. Okay. That's all I'm going to find there. Cosine of minus 1, that's going to be a quadrantal value, right? And I know from my sinusoids that cosine starts at positive 1. So halfway through its period, it's going to be at negative 1, and that should be 180. And I double check, and yep, there it is. The unit circle and the sinusoids are one and the same. It's so cool when your brain puts it all together. So this is going to be my third value of 180 degrees. And with quadrantal values, we don't usually have repeats. So this is our final answer. Should you recopy this so that these are in order, right? 120, 180, 240. I don't necessarily like that. I like to see how the first two came from the first one, and then this one came from that. I kind of like to keep them in the order that helps me connect them back to the answers. Whew. That was a workout, right? But kind of fun. I'm enjoying it. I hope you are too. Okay, there's one more. $85.3. Let's just squeeze it in here. We're going to go to another page anyway. Ready? Solve. Two tangent squared theta equals this is looking like this first problem. We've got tangent and secant again, right? This is on the left side. If I was a student, you know what? I wouldn't even, it's on the right side. I want it on the left side is what I meant to say. I wouldn't even write it like this. I would just bump it immediately right over because that's just annoying. Plus 1 equals 0. Change sides, change signs. Make sure you get your signs straight if you just flip it over. If you want to show your steps, that's fine. But at this point, it's fine with me if you just flip it over. Just be careful that you don't lose track of your pluses and minuses. Okay, we have our same limitation though, so let me write this down. We only want the first set of answers. Again, this is a great hint. Besides just telling me that, it's a great hint that my answer is going to be angles. I'm trying to find angles. That's what I'm going for here. And it also is a great hint that we're supposed to work the problem in degrees. There will be a day when we get radians up here, and then we have to, it's not a big deal though, because we have radians on our unit circle. So all you have to do is just read the other name for the angle. But that's where we find that out. Okay, again, we've got tangent squared, so that's the one we want to change. We're hoping there's a Pythagorean identity that links tangent to secant. We know there is because we did this in the last problem. It's right here, right? So we'll write, again, we write the source of the identity or the name of it. And that is that tangent squared theta equals secant squared theta minus 1. Somehow set that apart so people can see, oh, that's what you're tapping into. Now we'll put this in here. 2. And because this is a quantity, we're going to need the parentheses. We distribute, oh, I didn't point it to the right place there. 2 secant squared theta minus 2, right? Minus secant of theta plus 1 equals 0. Now we'll combine these like terms and we'll get finally a clean factorable. Oh, that's a 0, sorry. Lost my mind there. We get a nice, clean, factorable expression. Now we switch into algebra mode and we see this as 2x squared minus x minus 1 equals 0. I'm going to put a 1 there just to help me. Like I said, we multiply a times c, and that gives us minus 2. So we're looking for numbers that multiply to minus 2 and add to minus 1. So that will be, let's see, I want minus 2 and plus 1. Wait. Oh, yeah, I'm sorry. They multiply to this and they add to that. Beautiful. So now I split this. And I can write these in either order. It doesn't matter. I'm going to put the 2's together and the 1's together. So I'm going to write minus 2x plus 1x. And then I'll bring the other parts down. Right? These guys just go straight down. It's the middle one that splits in 2. And then we factor by grouping. I'll copy my 0, whatever. Let's see. I can take out a 2x. And I'll have x minus 1. And then this is exactly the way I want it, so I'll just do a plus 1, and then we have x minus 1 equals 0. That means either 2x plus 1 equals 0 or x minus 1 equals 0. And then I'm still in algebra mode, even though I'm taking up more space on the page. I try to keep it kind of tucked in so it's easy to see. This has to keep going though because I have to solve these for x. So this is going to be x equals minus 1/2 and x equals 1. Right? That's the end of our algebra section. Now we can go back into trig mode and secant. Yes, secant is the function that we're using. So we know the secant of x equals minus 1/2 and the secant of x equals 1. And we know that secant is reciprocal with cosine. So if we flip these, we'll get the cosine. So the cosine of x equals minus 2, right? We flip it, and we know that's not going to work because cosine is always between, this is one way to look at it. It's always between 1 and -1. And this is -2, and it never works. This is, by the way, absolutely the same truth for sine. Secant and cosecant can be bigger than that because they're the reciprocal. So they're writing their own rules. And tangent and cotangent, they're not in this club. So we can eliminate this one. We know that that's not true. If the secant equals 1, then we know that the cosine also equals 1 because 1, the reciprocal of 1 is 1. And now we're ready. Where does cosine equal 1? And we can figure that out by thinking of the sinusoids too, right? Cosine starts at its high value, so that's 0 degrees. And there it is, cosine of 1. So x equals 0 degrees. Oh, how satisfying, right? I mean, I don't know if you think that's satisfying. I think that's amazing. I'm so excited about that. I don't know, you guys. I just think these problems are so ridiculously fun because you look at them in the beginning and you think, that is impossible. There's no way. I have no idea. That just makes me tremble in my boots to even look at it. But then you break it down and you start going through bit by bit, right? First we do we substitute in the Pythagorean, and then you know what we did. But it's just fabulous how we can make it work. Okay, that's enough of advanced trig equations. I have something else to torture you with. Clock problems. Clock problems are another classic algebra problem, kind of like rate times time equals distance and boats in the water problems, coin problems. Clock problems are another classic algebra style problem. They're a little tricky, and in order to get these right, we have to review a little bit about the way analog clocks work, because we're talking about analog clocks. Okay, so here's an analog clock, and they are divided up by quarters, right? I broke it into quarters, and we're going to review this, exactly how they work. The top number is 12, and then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the hour hands, right? Or those are the hours. But there are minutes in here too. In between each of these numbers are smaller tick marks, right? Those are the minutes. Now, we have 2 hands on such a clock. There's a big hand and a little hand. The big hand counts the minutes. And the little hand counts the hours. And I wish I could tell you how much time I spent in my grade school classroom staring at the clock at the wall, watching things tick by. Okay, now what we want to do is we want to talk about the rates that these hands move at. The rate of the minute hand equals 1 space for every 1 minute. Right? And so we say the rate of the minute hand equals 1. 1 space per minute, and we can just break that down into 1. That's the first rate we need to understand. The second rate we need to understand is the rate of the hour hand. This one is a little bit more confusing. It goes five spaces in an hour, right? In the time it takes to go from noon to 1 in the afternoon, or midnight to 1 in the morning, let's say that, because that will make more sense for people who use the other style of time. It is going to move 5 spaces in an hour, 5 spaces in 1 hour, but an hour is 60 minutes, so let's say it in minutes. So that is 1 space for every 12 minutes. So we're going to say that the rate of the hour hand equals 1/12. Okay? These two rates are essential to all of these problems that we do, but here's the good news. They're always going to be the same in all clock problems. Each clock problem has its own wrinkles, but the rates of the different hands will always be the same. Yay. So make sure you have these rates locked in. Okay? 1 space every minute. This is the hand that moves fast. Tick, tick, tick. It's going to go all the way around in the whole, in 1 hour's time, it's going to go all the way around, right? This is the slow one. In an hour, it's only going to creep from one number to the next. That's only 5 spaces as we count those little spaces, all right? Okay, so now we're going to use these to help us solve some problems. How many of these are there? There's 2. 85.4. All right. The hands of a clock point in the same direction. In how many minutes will they point in the opposite direction? These problems make a whole lot more sense if you draw pictures. The hands point in the same direction at the starting. So let's just draw them in like this. Let's say it's straight up noon, all right? Now, we try to imagine what are they going to look like when they are in the opposite direction. Now, there's lots of times a day when the hands are opposite each other, right? But what's going to come up next? This is high noon. This one's going to start moving fast. The big hand's going to start moving fast. The second one's going to be slowly moving toward 1. So sometime around 12:30, this one will be like this. And the long hand will be like this, right? As it's going from 12 to 1. Let's just put them in. Right? And then this one will be down here. It'll be around 12:30. Right? If this is 12 o'clock. It'll be around 12:30. John's asking us to find out exactly what time it will be. Okay, so we know that, oh, there were a couple other things I wanted to tell you. No, I'm good. What we have to do is we have to set up some equations to find out how many spaces these hands are going to move, because that will allow us to figure out the time. So, what we do is we say that the rate of the little hand times the time of the little hand will be a certain number of spaces. Okay? We know the rate of the little hand, or I like to call this the hour hand. The little hand is the hour hand, and I think that's a better way to say it. John always says little. I think hour and minute hand makes a lot more sense. That will tell us how many spaces that it will move. The minute hand has to move, it'll move the same number of spaces, but it has to move 30 more in order to be opposite, right? It's going to have to move this small amount. This is how many the hour hand is moving. And the minute hand has to move that many plus 30 more. So S is the number of spaces that the hour hand moves. Right? It has to move that same little chunk and then 30 more so that they'll be directly opposite each other. All right? The rate of the hour hand, we already figured out. The hour hand is 1/12. The rate of the minute hand is 1. And we know that the 2 times for these, the time of the hour hand has to equal the time of the minute hand, because we're not going to let one move longer than the other. It's the same. This one's always the same, right? So here is what you need to know in order to set this up. We're always going to have these two. These rates, they'll always be the same. This equation, I believe, is always the same. The hour hand rate times the hour hand time equals S. And then depending on how the problem is, this is the hardest one to write, because this one has to be custom made to whatever situation John is setting up in the scenario. Now we're ready to start substituting. Okay, so what we're going to do is we're going to substitute the rates into these problems. So step 1. All right, so we'll put these 2 rates into these 2. And then because time is equal, we can simplify the time of the minute hand and the time of the hour hand into just plain T. Okay, and then there's a third step that I'll add when we get to the next page. So what we'll have is we'll have t, because I can drop the h, over 12, because this rate is 1/12. So this will become t over 12 equals s. T over 12 equals s. And then this other one, I'll put the rate of 1 into this, and we'll drop this, and we'll say 1t, or just t, equals s plus 30. Okay? Now, what we will do for our third step, I'll write it here. Sorry, my book's falling out of the frame. This is another one of those cases where words do not explain what I'm trying to say. What we're going to do is we're going to set both equations equal to s, and then we'll put them equal to each other. So this one's all good to go. This one will change to t minus 30 equals s. And then we'll be able to say t over 12 equals t minus 30. That's what I mean by set them both equal to s, right? There's our s now. And then we're able to take those parts that are both equal to s and set them equal to each other. Okay, fabulous. We're almost there. And now we just algebra it up at this point, okay? So we will cross multiply, and we will get t equals 12 times t minus 30. And we will get and let's see, let's bring this t this way, and let's add 360 to both sides. Cancel, cancel, and we get 360 equals 12t minus t, 11t, divide by 11. These are the kooky answers we always get. It's not very satisfying. T equals 360 divided by 11 minutes. That's how, here, let me write minutes in here. That's how much time will pass that's how many minutes will pass until they're pointed in the opposite direction. 32 and 8/11 of a minute if you care. I do not need your answer to be in this form. I'm perfectly happy with this, but 32 and 8/11 minutes. What that tells us is that if 32 and 8/11 minutes are passing, that tells us that, what did I say? 32 and 8/11 minutes. That's our answer. That tells us that this little chunk of time is 2 and 8/11, right? That's this. And then there's the 30, so that the total time down here that the minute hand will have passed is 32 and 8/11 all the way to there. Weird, right? Kind of cool. I don't know if you see yourself ever using this calculation in real life. More likely you'd just like get out the timer on your phone and set a stopwatch. But anyway, like I said, these are classic algebra problems that everybody's like, oh, clock problems. And I have seen them in the advanced sections of some placement type tests. standardized tests. They are considered really hard. So it's not the sort of thing that you'd have to do on every test, but yeah. Okay, it is 3 o'clock. Okay, what does 3 o'clock look like? The big hand is pointing straight up at the 12, and the little hand is pointing at the hour of 3. Okay, I'm also gonna write down the rate of the hour hand is always equal to 1 over 12, and the rate of the minute hand is equal to 1. That's always true. It's so nice to just write it down from the get-go. And we also know that the time of the minute hand equals the time of the hour hand. I'm also gonna say again that if you look in the book, John often uses big and little. That's too confusing. I don't like that. I like to use hour and minute hand. The hour hand is the little hand, the minute hand is the big hand, but I don't like it. I used to teach this using big and little like John, and it was too confusing, so I've switched. Trust me, it makes more sense. In how many minutes will the 2 hands of the clock point in the same direction? Okay, so I'm gonna go down this time. Before I was always going across, but I wrote all this up here. So let's see what's gonna happen. Again, there are many times of day when the 2 hands point in the same direction, but we're trying to find when will it happen next. What's gonna happen is this guy's gonna come down and meet him, but he will no longer be pointing directly at 3. They're gonna be, on their way to 4. Something like this, right? If this is 3 and this is 4. This is 3 and this is 4. I might not have the proportions right, but that's a sketch that helps you see, right? So I can see that this big hand is gonna have to come as, the little hand is gonna move this far. That's how far the hour hand will have to move. And we'll call that S spaces. And the big hand is gonna have to travel 15 spaces more, right? So the minute hand will have to be S plus 15. That's the hardest part of these problems, is trying to figure out what's the relationship between how they're moving. So I know that the rate of the hour hand times the time of the hour hand is gonna equal S spaces right there. And the rate of the minute hand times the time of the minute hand is gonna have to be S plus 15. And now all my worst nightmares are happening because I have an S and a 5. Oh, my S's look too much like 5s. It drives me crazy. Okay, so what are our steps? Number 1, sub these rates and this time, which we'll just call T, into these. So I'm gonna rewrite these 2 over here. I'm gonna write T over 12 equals S, that's this one. And then I'm gonna write 1 times T, so just T equals S plus 15. Now I'm gonna solve both of these for S. This one's done. I'll just have to bring this over. T minus 15 equals S. And then I'm gonna use the 2 S's to stick these guys together. T over 12 equals T minus 15. If this is starting to feel similar to the other problem, you're right. And that is one of the comforting things about these clock problems, is that they are quite similar. These 3 equations will always be the same, and this one will always be the same. 1, 2, 3, 4 of the 5 are always the same. This is the one that changes, and we have to use the diagrams to figure out how is that minute hand gonna behave? What does he have to do to meet the challenge that is laid out in the problem? Now we just cross multiply. T equals 12T, I'm gonna distribute in my head. 12 minus 15 is what, 180? And so I get, let's see, I'll mentally subtract the 12t and then multiply by -1, so everything will become positive. I get 11t equals 180, right? I bring this over here, I get minus 11t. I turn it positive. I'm left with the minus 180 over here, but I multiply by -1 and turn it positive. T equals 180 over 11 minutes. Remember, this is a perfectly acceptable answer from my point of view. That improper fraction is lovely, but if you want to just make sense of it, this number is 16 and 4/11 minutes. And let's take a look at how that makes sense. 15 of those minutes are going from here to here, right? And so that means this little chunk would be what? 1 and 4/11. Right? Because it was 15 to get us this far. There's the 15. And so this, we don't have to solve for S, but I just think it's interesting to look at how the time breaks up. It would only take 1 minute and 1 and 4/11, 1 and what, a third of a minute for this hand. I've got it pointing almost all the way down to 4. It wouldn't be. It would be much closer to the 3, wouldn't it? You don't have to figure that out. I just think that's an interesting part. This is your final answer. Again, I am fine with improper fractions. I think John typically does this, so you can just do a quick cross-check, multiply those, and add that, and make sure you get the right answer. Yay! Clock problems are done. We're not going to add to that. That's as far as we take clock problems. Those are hard. Those are hard. This was a very difficult lesson. If you're hanging on by your fingernails and fighting to make sense of it, you're doing a fantastic job. Yay, go do something fun. You've earned it. And I mean, do your homework too, but do something else that's fun. Thank you, goodbye.